Hi everyone, thank you for choosing physics over lunch. I also made that decision a couple times. My name is Yuval Frid. I'm going to finish my PhD soon in particle physics in Tel Aviv University. And my research was focused on implementing machine learning tools in the Large Hadron Collider at LHC at CERN. I'm going to give you a taste of some of the challenges we are facing at the world's largest experiment and how machine learning helps us overcome them. I hope that by the end of this talk, you will see that our data challenges are quite similar to what you have in the industry, with some small differences, and that machine learning can do a lot more than just write our papers for us. And just as a disclaimer, I'm not here representing CERN or the university. Everything you see here has already been published or things I've done myself. So I'm sure you're all wondering what's a PhD student doing at code.talks. Is it because of some great award that I've won, or maybe some great discoveries? So the truth is, the guy you saw at the talk, the introduction talk, the host Martin, is my brother-in-law. And if my face looks familiar, it's because he made sure to put me on the front page, right there. Yeah. Now that we got this out of the way, let's try to understand what do I mean by saying particles. We have many particles in our lives, some we can see, some we can't. And if we look at the scale of how small we're talking here, a lot of times I like to compare it to my little Jack Russell mix, Suki, which is about 0.5 meter in size. And if we look at the logarithmic scale in meters, starting at around 1 meter, so Suki is right at the top, about 100 times smaller than her. You will see particles of sand that we can see with our own eyes. 100 times smaller particles of dust that we can see when there's light coming in. That's about 10 microns. 100 times smaller is corona, which we can't see, but I'm sure you all know how it looks like in a microscope picture. And 1,000 times smaller than that, what used to be the smallest particle until about 150 years ago, is the atom. But the particles I'm talking about are 100,000 to 100 million times smaller than the atom. And the interactions we're trying to look for are all the way at the bottom. And all of these particles exist here in this standard model, sort of periodic table. Some of these you've heard of, like the electron. Maybe you heard of quarks, or a photon, which is the light around us. And the latest discovery was the Higgs, the so-called God particle that gave us mass, thankfully. But as good as this model is, and as much as it's describing everything we see at the collider, we know it's not complete. There are things we can't understand at this scale, and they're not included in this model. For example, gravity. We have no idea how gravity affects particles at this scale. We can't explain it. Dark energy, dark matter, and a lot of other things you might have heard of in sci-fi movies. So what we're trying to do is find where this fails. And the way we do this, the first thing we do, we accelerate protons to almost the speed of light. And I say almost, the speed of light is around 1 billion kilometers an hour. We are about 10 kilometers an hour too short. So insane speeds. We smash them against each other. These are very, very tiny particles, which means the chances of two protons colliding is about the same as me winning the lottery twice in a row. So what we do, we take 100 billion of them, condense them into a very, very narrow beam, and we send two of these beams to hit each other. So out of these 100 billion pairs, we get about 50 collisions, which is in itself a challenge. We record billions of events. For us to announce discovery, we have to be absolutely certain. If there's a 1 in a million chance that we are wrong, we won't announce it. We need what is called a 5 sigma discovery. That means 5 standard deviations away from the expected value. which is 1 in 3.5 million chance for statistical deviation. For that, we need many, many events. And we reconstruct the full process from the detector signals. So I want you to imagine two cars crashing against each other and have been towed away. And now you need to understand exactly what happened there using only the tire tracks, some broken glass, maybe a mirror that fell. And I need you to know which model the car, from what year, and what was the speed of these cars colliding. And the way it looks like is chaos. Each of these yellow lines is a particle flying somewhere inside the detector. Each of these squares is a measurement of energy. And from these lines and squares, we're trying to reconstruct everything that happened inside. In general, we can sum the whole process from the moment these particles collide until the moment we announce we found something, or most likely didn't find, into 3 steps: acquisition, identification, and analysis. And it's not too different from what you might do in your own industry. So starting with acquisition, let's say that you are trying to understand your customer base better. You're uploading a post on Instagram and you're writing, anybody commenting here reward might get a reward. You get 1,000 people commenting. Acquisition is the part where you go into each of these profiles and you collect everything you can. Every image, every comment, every like, whatever you can, any raw data. For us, it means collecting all of the data we have at this event. Now, the chances of something interesting happening when 2 protons collide is, again, like winning the lottery. It's 1 in a million, 1 in a billion. So we are doing collisions at 40 megahertz. That means 40 million collisions per second, about 25 nanoseconds between collisions. This gives us a data volume of 60 terabytes per second. From a quick check on Google, that's about 5 times faster than the global data volume of YouTube right now. And we're not streaming it, we're storing it, which is much harder. So we have too many events to save, but also most of the events we just don't care about. So what we do is doing filtering online. We make a decision in less than a microsecond. Do we save it or do we throw it and lose it forever? These are very fast algorithms. They can't be too complicated. We have a microsecond to make a decision. We do it on hardware, not on software or firmware, because again, it has to be very fast. And it used to be very basic. In 2015, a particle called the tau particle, it's a sort of a heavy electron, had this system. Each one of these squares contains around 50 different signals that I just sum up into one area. I'm looking at the sum of 2 green squares, trying to figure out how much it is, how much bigger is it than the yellow ring around it. If it's big enough, pass it. If it's not, throw it away. 2 years ago, in 2023, a new algorithm was introduced, thanks to us being able to split this yellow square into many more channels, giving us a lot more data. And the new FPGA modules, that's a field programmable gate array, it's a sort of chip we can write our algorithm on, allowed us to insert a boosted decision tree, BDT. It's a very basic machine learning algorithm. Basically, you insert many features and you get a score. So one of my colleagues named David took these small rectangular cells. Each one of them now contains 5 sensors instead of 10. And he made symmetrical sums. That's the color pattern you see there. And he put all of them into a BDT. I can't show you results, unfortunately. And I'm working right now on something that will hopefully happen in 5 years, in the next big upgrade, where we might even have a small neural network there. But even though it might sound not too hard, I want you to understand that the full data pipeline, everything going from recording the event to storing it, goes through a lot of steps. There's a lot of different particles with different algorithms. Each of these rectangles have dozens of people, scientists, physicists, engineers working on. Identification. So in our analogy, we collected everything we could about the users. Now we're trying to segment them. We want to understand the gender, the age, the hobbies, interests, anything we can to build the full picture. In our case, we want to understand what was the particle involved. This is extremely hard because, like I said before, we don't see it directly. And when we store it, the energy deposits are actually blurred by physical processes. So if we take, for an example, the photon and the electron, we make the detector from a material that causes them to make an interaction and slowing them down. For the photon, it will be pair production. It splits into two electrons with smaller energy. And for the electron, it emits a photon. It's called the Bremsstrahlung. And what we end up with is a lot of small particles instead of one heavy one. And then we can measure it, and it looks something like this, a cone of energy with some blurry shape. Now, an even bigger problem is that some processes, like this guy, pion 0, it's very common, almost always splits into a photon pair. And when it's fast enough, these two photons have such a small angle between them, it just looks like one big cone, something like this. So we now have to distinguish between these two images, and one of them is an actual photon, the other one is two photons that are very highly collimated. And what we used to do is try to figure out what are the characteristics, the width in X, in Y, maybe the depth, the amount of energy, all kinds of mathematical values, and put it into a BDT. If you would look at it at 2 dimensions, can you see from there? If the blue dots are the signal we're looking for and the red dots are the background, and we have only 2 variables, we will ask which is the region where there's the most ratio between blue and red, the most blue for red. And we will make a cut. And every red dot we see inside the region is our false positive, and the blue outside is what we miss, the false negative. And since this data can be restructured into images, I thought it would be amazing to just use something that's already existing, the ResNet architecture, residual network. This is a machine learning algorithm, a neural network that is based on convolutions and skip connections, allowing us to make it deeper. But instead of training it to classify dogs, cats, mouse, or whatever else, I classify it to distinguish between signal and background. When we look at the results, if we see the y-axis, that's the efficiency of detecting. The energy is the x. It's just easier the more energy you have. And the old algorithm you see in blue and purple is half as efficient as the ResNet in green, meaning for the same amount of contaminated data or false positive, we get twice as much real data, giving us a lot more accuracy for the next step, analysis. So in our analogy, we collected all the data, we segmented the users. Now we're trying to understand what is the underlying picture. Maybe 50% of the people that commented are men between 25 and 35. How do we change our strategy? How do we make marketing campaigns and stuff like this? So in our case, what we want to do is to distinguish between background, that's everything we already know, and signal, what we don't know and what we're looking to prove. The way we do it is we make simulations separately, and we model them with some functional form. So let's say we're looking for the Higgs, for example. That's what they did 15 years ago. We are asking, how will the Higgs look like in my detector? It will look like 2 photons in a specific shape. In this case, it's the blue bump you see there. We try to analyze what is the shape of this bump. It's some sort of Gaussian or other function. And then we ask ourselves, what would we get from the model if there were no Higgs around? What is everything else that could look like a Higgs? Anything else that can give me 2 photons? In this case, it's the red measurements. And we see that there's a smooth descent, and we need to model this function, like you did in high school maybe, to find it as a sum or a multiplication of an exponential or logarithm. And if we look at the analysis they've made, you can see that they modeled really well the background, and then in around 125, you can see this bump. And this bump is strong enough to announce discovery. And the most important thing when you do this is to make sure that you have a very accurate background description. In my master's, I had to spend about 3 months on a very complicated function. It had about 10 variables. I hated every moment of it. I thought it's a waste of my time. And I decided that I want future master students to not suffer the way I did. So it's even harder, I didn't say it, if you have low statistics, you get these strong fluctuations, and it's really hard to say which of these colors, the red, green, or blue, are the actual fit. So as a PhD student, I decided to pick up these 3 equations. wrap them up nicely in a PyTorch code, and creating a model that feeds on the evidence, in this case the samples we measure, and slowly learns what is the accurate shape. So we start with the black line, entirely flat. Every iteration we go, as I feed it with the evidence, it slowly learns what is the correct shape, which is the dashed line. This allows automated, fast, and accurate modeling, and hopefully it can also speed up analysis in the future. I'm still waiting for it to be picked up by one of these analyses. So some buzzwords that I'm sure you will ask me about, because this is all the hype today. For us, simulations are very expensive, very time-consuming, and it can take up to a minute for a single event. It's very heavy calculations, and we would love to use Gen AI. There are some projects working on it. Oh, there we go. So the first step to do this generation is to do an autoencoder. We feed as input the image I showed you before. We encode it or compress it into a latent space representation, meaning we now have the same amount of information in a lot less variables, and we decode it back. We decompress it into the full image. Once we train this autoencoder to replicate our data well enough, and we know that we have enough stored in the bottleneck, in the latent space representation, we can throw it into another type of network called normalizing flow. This is a network that takes on very complicated distributions that we have no idea how to sample from, learns them, and transform them into a normal distribution, which is the easiest thing you can imagine. And the beauty is that it's also reversible. So once I train it to go from very complex to very easy, I can generate with one line in Python the values that I want, transform them into the bottleneck, into the latent space representation, and decode them back. And I created an entire pipeline from a single line in SciPy or NumPy into a full reconstructed event. Another thing that came to our lives with ChatGPT, transformers. So these are algorithms that are mainly made for finding connections between different inputs. If we're talking about a text, it will analyze each word or token and try to understand the meaning behind connecting these words together. In our case, it can take several clusters of energy that we have no idea where they come from, learn them, and categorizes them based on events. So now we know that the two on the left are actually coming from the same event. The one at the top come from a different collision, and the three reds are from a third collision, giving us a much better understanding of what is actually going on. Unfortunately, we don't have enough time for the Lagrangian, but I'm sure it's not too big of a deal, right? Maybe next year. So the key takeaways from today is that just like in the industry, acquiring the data is hard and analyzing it is hard. And in our case, discovering new physics is really hard. But machine learning makes it easier, so we don't have to sacrifice speed for accuracy, and we can just multi-track drift to discovery. Thank you very much. If you have any questions about physics, machine learning, any cool job offers for next year when I finish my PhD, you can email me, add me on LinkedIn, or just look for me in the cinema. I will probably be here the whole day and tomorrow. Thank you. Yeah.